Swayam Prabha. Digital India. Educated India.
Welcome everyone to this NPTEL online certification course on techniques of materials characterization, and we are in module 12. This is the last module and we are discussing about X-ray diffraction. This is lecture 2, and now until up to now we have discussed about the various factors that basically modifies or that affects the intensity of an X-ray diffraction beam, and we have seen starting from structure factor. Starting from atomic scattering factor, we then built up structure factor, we discussed about the multiplicity factor, we discussed about the temperature factor, absorption factor, and lots of other different factors we discussed about them, that how the intensity can get modified, certain reflection, certain diffracted beams will be present, certain others will not be present. And then we have obviously before that we discussed about X-ray source, and we discussed about Bragg's law, the required conditions for diffraction, and all of these things. Now onwards, so the remaining 4 lectures we will be concentrating on understanding the X-ray diffraction peak or X-ray diffraction profile from a real specimen. And when I mean real specimen, mostly we concentrate on powder specimen or solid specimens, but mostly on a normal regular X-ray machine that possibly you will be seeing, Bragg-Benton geometry kind of X-ray diffraction machines that you will be seeing, and the X-ray diffraction profiles that we will be getting. We are not discussing, as I last lecture if you remember, I told that there can be many different geometries of X-ray diffraction, Laue diffraction, Debye-Sherrod diffraction, and so on and so forth. We do not go into all of this. Very regular, and if this sounds familiar to you, the powder diffraction method. You can use a solid specimen instead of a powder, but basically it is the same powder diffraction, the kind of X-ray diffraction profile that you get. So, we will try to understand various aspects of this X-ray diffraction profile from a real specimen, and why we are getting that, what we can understand out of it, so on and so forth. So, here first we will try to understand various aspects of diffraction from a real specimen, then measurement of FWHM, what does that mean, full width, half maxima, we will discuss, and then we will discuss about something called line broadening. Line broadening first, and various sources of line broadening. First one we will discuss about the instrumental sources, and then we will discuss about certain sources which are inherent to the specimen itself, and that will reveal possibly many information more than just a identity of crystal, or more than just a solving the crystal structure. We will be able to understand many more aspects about a material. So, we will discuss all of these things, but let us first see the diffraction from a real specimen. How does it look like? And I assume that many of you have possibly, particularly the research students, many of you have possibly seen a real X-ray diffraction profile. You may be having a powder sample, you may have taken a piece of solid specimen and you put it in a X-ray diffraction machine, and that machine finally give you this kind of a graph, which is basically an arbitrary unit. This side it is the intensity, and this side you will see the 2 theta, and the heart of this is definitely the Bragg's condition, n lambda equals 2d sin theta, and of course the intensity part is determined by these various factors we discussed so far. Fine, that is it. Now, the point is that why I am saying diffraction from real specimen, why I am stressing on this fact that real specimen, what is real specimen and what exactly happens for a real specimen. Okay. So, if you compare these two X-ray diffraction profile, and this is also possibly you have seen in if you try to solve this X-ray diffraction profile, you want to identify the phase, you want to know the lattice spacing and so on. If you want to do that, what you try to do is to first you bring something called JCPDS, or various other names are there. This is basically a database which gives you the X-ray diffraction profile of a corresponding phase, or element that you are interested, you can bring out that. But basically this X-ray diffraction profile you yourself can generate. What you get from the database is actually a real specimen, again a real specimen under idealized condition and all, a real specimen which you try to match with your specimen, but you can generate this one. How you can generate this? Okay. The idea or the way you can generate this is very simple. You just use the Bragg's law, that is it. You do not need to do anything else. You can generate an X-ray diffraction profile for any material. How is it so? All you have to do is to know the crystallography of that material. Any particular material you take, you know that is a BCC structure or FCC structure, simple cubic structure, whatever it is. You know the structure, you know the symmetry, you know the lattice parameter A, B, C and so on. That is it. That means, in this n lambda equals 2d sin theta Bragg's law, you know the lambda, that is from the instrument you know what lambda you are operating on, and we will see there are, even this lambda is not a constant, that brings another kind of an error. But for that moment you assume that lambda is purely monochromatic, excellent monochromatic X-ray beam, and one single lambda value you are getting, that is it. Then what you know is d value. Of course, you know the symmetry of this material, you know the unit cell, you know the lattice parameter, everything you know. So, you know the d spacing for different lattice planes. If you are interested for say 100 plane, you know the d value, and let us assume again, as I said, that you are using a standard crystal unit cell, you are using BCC, you are using FCC. So, you know the relationship how to calculate this d spacing from the lattice parameter. Okay, fine. So, you know the d value. All you have to then calculate, you know lambda, you know 2, you know d, you have to calculate the sin theta value. So, you know exactly at what sin theta you can expect the diffraction to happen, and then there, okay, you mark that here, fine, done. You know the exactly which position you will be getting these peaks, first thing. Okay. Next thing what you can do is that you can find out even the intensity of this theoretically, if you know the structure factor. So, structure factor and multiplicity factor, if you remember, I said structure factor and multiplicity factor, these two are related to the crystallography of material. So, you know the crystallography, and you can find out the intensity of say 100, 002, 101, that is 110 type peak, all of these peaks you basically know, okay. Their peak intensity also in relative unit, you know the peak intensity, what should be the peak intensity of say 100 plane, what should be the peak intensity of 002, 110 type or 111 peak, and so on and so forth. So, you can ideally generate this entire diffraction pattern. When I say ideally generate, what you assume is an ideal material. Ideal material means a material which does not have any imperfection, or in other words, the material which does not have any kind of defects into it, a complete ideal material where only Bragg's law is determining the diffraction, where exactly which direction diffraction should happen, means sin 2 theta, and only structure factor, multiplicity factor, these are determining what should be their intensity, that is it. Then you can very well generate this entire thing, and if you notice, this is giving you as a line, that means at a particular 2 theta value you are getting this diffraction, and that has a particular intensity, fine, okay. So, this is completely generated by you, you can take an Excel sheet and generate this entire diffraction profile, then you plot it, okay. Problem is, if you try to see for the same material, this is shown for a ZNO, zinc oxide nanoparticles, okay. If you want to see this, what you will be seeing is a complete different picture altogether. You will see that your peaks are now not a single line. If you are fortunate, okay, you will be getting the maxima of those peaks at least in this exact positions. That also is not guaranteed, because that depends on many other things. But let us say you are very lucky, you get your maximum exactly at the sin 2 theta position where this one is showing, fine. Even with that, you will see that this is not a line function. This has a certain width, this is some other kind of function, this is some other shape altogether. The peak has a certain width, a finite width, number one. Second thing, what you can notice is that the structure factor and other factor, the intensity that you calculated is not matching here. Here, according to this, 100 peak should have a higher intensity than 002 peak, right? But you can see here that is exactly reverse. So, you are getting completely different intensity. Now, the intensity part is getting modified over and above structure factor and multiplicity factor. The intensity is getting modified by other factors we discussed, that temperature factor, absorption factor, so on and so forth. Many other factors are there. There is something that we didn't discuss. If time permits, I will try to discuss something called texture factor. That is also there, and that is invariably that used to be there for a solid specimen, texture factor. Okay. But all of these practical factors will modify the intensity mostly. Plus, there are many other factors which are related to the material itself, the defects in the material, because ideal material or this one is derived for an ideal material which does not have any kind of defect, any kind of imperfection, which is absolutely completely a defect free. Now, if you remember our discussion about the temperature factor, there we said that the entire this intensity calculation is done, or even the Bragg's law derivation is done with the assumption that all the atoms are fixed at their mean position, but the temperature itself will cause this sort of something vibration at their mean amplitude position, and that itself we have seen how that can modify the intensity. So, same way it can modify peak positions and all that also we have seen that it can do. So, these are the kind of defects, or these are the kind of scenarios which are taking this diffraction phenomena from a perfect idealized condition to a real condition. In a real material where the diffraction experiment is possibly carrying out at a higher temperature. So, you cannot neglect the temperature factor. It is carrying out on a real some certain thickness of the material. So, you cannot neglect the absorption factor. It is carrying out on a specimen which has a finite size. So, that also is kind of an imperfection. For an ideal material, it has to be infinite, just like a definition of a lattice which says that it is an infinite array of points. When you make this, break this infinity, the lattice is not expanded up to infinity, that itself is a defect or imperfection in the real specimen. Then many other imperfections, many other defects can come, and that will basically modify this entire diffraction profile that you theoretically generated for an ideal material, and what you will be really getting is something like this, which is close to your ideal condition, but deviated because of certain factors which are related to the real specimen. Some of them, and those factors we will be discussing one by one. We will try to understand what basically gives us this kind of an X-ray diffraction profile instead of this one. So, intensity part, as I said, mostly it is because of those factors we already discussed: temperature, absorption, polarization factor. All of these things are related to this this one, the modifying the intensity of this peak. So, that we will not discuss in great detail, but we will be discussing mostly about this position, where this peak and why the finite thickness of the position comes, because that will tell us more story about this entire real specimen. That can help us to tell us some more about the specimen itself. Now, the first thing is, if we look at this Bragg's condition itself. So, Bragg's condition, as it says, if it is followed, if Bragg's condition is completely true for an ideal specimen, then you are getting only at intensity at a specified position, right? That is one thing you should not get, because what Bragg's law says is that an atom, we discussed about that, if it is an isolated atom, the atoms scatter X-ray beam in all possible directions. But when that atom is a part of an unit cell, because of the crystalline periodicity, because of the crystalline arrangement, what happens is that the X-ray beams are getting constructively reinforced along certain directions, very specified directions, and all other directions there is a imperfection. Certain direction there is a destructive interference, complete destructive interference. Most of the other directions there is an imperfect one or partial interference that is happening. So, that means in an ideal condition the Bragg's law is valid only in an ideal condition the Bragg's law is valid, and there only we are getting intensity along certain directions, okay, and that is related, that the Bragg's law has to be valid is related to this periodicity of this crystals itself in the first position. So, anything that disturbs this periodicity of crystalline structure or this periodic arrangement of atoms, regular interval atoms are arranged with a symmetry, with a specific distance and all. Anything that changes that periodicity, anything that takes it away from this periodic structure will cause an imperfection, will cause an defect, and that will take you from an idealized specimen where Bragg's law is exactly valid to a condition where wax law is somehow relaxed. So, now we have to see what could be this different type of defects in the real specimen, which makes the real specimen and which is taking it away from an idealized condition, and that will help us to understand, again as I said, that why we are getting this kind of an X-ray diffraction profile. Okay. Now, as I said, constructive interference is a consequence of this periodic arrangement of atom. Same way, destructive interference is also a consequence of this periodic arrangement, because just like when if you remember, when there is this the path difference is exactly an integral multiple of lambda, we are getting a we are getting a constructive interference. And remember the base centered versus body centered example when we are deriving the Bragg's law. That time we saw that if same thing can happen if the path difference is half of or 1/2 of lambda, then there is a complete destructive interference. So, basically destructive interference is as much a consequence of periodicity of atomic arrangement as the constructive interference. So, these are the two extremes, and in between there is partial interference. Okay. So, that means when we are having these defects inside the material, we are basically going from perfect constructive interference case to a more imperfect one and closing towards the destructive interference. But again, perfect destructive interference also is a consequence of periodic arrangement. So, defects and imperfections will not take us there also. It will be somewhere in between this constructive interference and destructive interference, and then what we will have is we will have some diffraction or scattering or certain intensity at non-Bragg's angles when a crystal imperfection is present within the material. Okay. So, something like this what we try to tell here, this is the crystallite, this is a case where all the atomic planes are perfectly placed and the d spacing between them is also perfect. This is constant throughout the material, and in this case now we are getting these peaks exactly at the same position, something like this. We are getting the peaks exactly at the middle at the same position, but when we have some kind of a defect present in the material, the atomic planes are not any longer continuous, they are not having the same d spacing, and what that results is that now we started getting this peak to be broadened. These peaks are not as narrow as this line function, they are now getting bigger and bigger. That means the diffraction is satisfied for non-Bragg's angle. So, this point or this line is showing you exact Bragg's condition, and you are trying to now started getting certain intensity at non-Bragg's angle also. That means you are getting basically partial interference, you are from a complete constructive interference, you are going away to partial interference conditions. Now, the point is, compared to this ideal condition, the imperfections within a real specimen is order of magnitude lower. Usually the imperfection, the amount of imperfection in a material is order of magnitude lower than the perfect nature somewhere else. That is why more or less you get this kind of intensity maxima more or less lies at exact Bragg's angle, and what you afterwards what you get is basically this non-Bragg's angle conditions, diffraction, certain intensity that occurs due to the partial interference, and you get basically a broadening. The peak gets broadened, the peak becomes from a line function, the peak becomes some other kind of function, maybe a Gaussian function, Lorentzian, and many other functions are there. We'll briefly discuss about that, but you are getting this little bit broadening, peaks are getting broader in the 2 theta axis. So, that is what is mostly the effect of imperfections on a material, and this the diffraction pattern from a real specimen is all about the presence of these imperfections. Okay, fine. So, the defects, what kind of defects we are talking about? There can be various type of defects, that's you can just name it as many as possible, point defects, 1D defect, 2D defect, 3D defects, all kind of defects will have its effect on the diffraction profile. So, but here the main few defects we will be talking here. So, for example, the most important, one of the most important defect in the material or in the real specimen is basically the grains, the size, the finite size of the materials, the first thing there. As we discussed the Bragg's law, if it is an idealized material, it has to be an infinite array of these points, just in order to have exactly like a line function. But our crystals are of finite size, that means they have interfaces. If it is a crystal, if it is a single crystal, you will have interface with, let us say, air or other material, there will be this interfaces, and if it is a polycrystalline material, you will be having these grains, which are essentially a single crystal and then separated with others from by this grain sizes. So, basically this size of the crystal itself, that it has a finite size itself is an imperfection within itself. So, the size effect, this finite size of the material, that itself is a defect and will affect the peak, the X-ray diffraction profile from a real crystal. And this, the best way we can imagine this, or best way we can understand this, if we compare the X-ray diffraction profile from a crystalline material and with that of a liquid or amorphous material, which we can think of is another extreme, or a monoatomic gas, which is another extreme where there is no perfection, there is no order itself. So, from a complete ordered condition to an disordered condition, and that itself will show us that effect of this size, the finite size, or effect of order present in the material. Another kind of defects that we can think of, mostly happens for metallic materials, is the dislocations. The dislocations or the strain. In broader context, we can talk about the strain, or in other context we can talk about the dislocation. So, dislocations is a line defect, that all of you know. Dislocations is a line defect, and mostly within the material that they are present, the dislocations are present wherever they are present, they are associated with strain fields and so on and so forth. So, there could be strain associated within the material, even if it is a crystalline material, within the material there are strain associated with it. So, and this dislocation, where the dislocations are too many in number, they form their structure and they further divide the material into smaller units. So, even within the grains they form this kind of structures. This is a thermomechanical process, thermomechanically processed iron, and this material you can see that this has typical dislocation structure, which we call substructure. We will discuss about that maybe in the next lecture. We will discuss about this dislocation substructure, but this kind of just because of the presence of dislocations, high amount of dislocation, we are getting this kind of a structure within the material. So, the grains are even more subdivided into smaller crystallites. So, size is getting decreased. So, all of these are defects, all of these are an imperfection within the material, which are basically taking the real specimen away from the ideal or idealized conditions. Okay. As I said, most of this effect of these defects are seen in the broadening of this peak. So, instead of a line function, the peaks becomes like a different or peaks becomes with a different shape and can be fitted with different functions, and usually they becomes broadened, their size increases in the 2 theta along the 2 theta axis. So, the way this is measured is called FWHM, full width at half maxima. So, this is measured, usually this is measured in radians. So, you must remember that this is an angular width, the FWHM. So, if you take this real diffraction profile and you try to measure their FWHM, basically what you are measuring is this axis, along this axis, which is given in terms of 2 theta. So, the angular width, the width you are measuring for a peak is basically the angular width, which is normally given in a radian, or you can express it in degrees as well. Okay. And this is definitely not a linear width. Many people I have seen, even the students I deal with, many of them, they did do this mistake. They measure it along a scale, of course, they measure it and they come back to me with the FWHM, which is they report it in terms of some unit of length. But actually this should be measured in terms of the width or this measured in terms of the angle, 2 theta angle here. Okay. So, the way this FWHM is measured is actually basically at half the maximum intensity, where the intensity drops, the maximum intensity drops to half the value, there the width, we measure the width of a peak, and that is why it is called the full max width. Full width means from this to this angle where the intensity drops exactly to half, from this angle to this angle, this is the full width at half maximum. Okay. also what we will be seeing that we can also measure this width of the peak by measuring these two angles, by taking the difference of these two angles, where this one becomes, the intensity becomes basically 0. So, this intensity, where the intensity becomes 0 or very, very small, that 2 points, if we take the difference between these two angles, that also is giving us the full width f at half maximum b. Okay. So, this is the way of measuring the width of a peak, and as just now we understand that ideal condition, in ideal Bragg's condition, this is a line function. So, anything that increases this width of this is the broadening basically, and what we are interested now onwards is what causes the broadening. So, the FWHM is basically the measurement of this broadening, how much broadening has happened, and now we will be trying to understand what causes this broadening, what takes it away from a line function which is here and making it some other kind of a shape, other kind of a function. Now, this itself, this understanding this broadening phenomena itself is a real big area of research, and this is known by many names. One few of the names that you may be here heard of is something called Rydberg refinement, where you basically try to understand this peak broadening from different sources you consider, and you try to match these peaks. All of these processes basically involve matching this peaks by a suitable function. Something like, some examples is given like Gaussian, sometimes the peaks are Gaussian, sometimes they are Lorentzian, you can fit it with Gaussian Lorentzian. There are many other different functions that you can pseudo-void, various type of functions you can bring and try to match this the peaks, and in the process of matching you imagine different type of sources of this broadening, peak broadening, and the relative contributions of that. From there you can find out that what exactly is causing this broadening, and you can extrapolate that in understanding many other things, many things about. Just one example is you can understand the type of dislocations present there, or the dislocation density that is present within the material, the type of, sometimes even people are trying to understand the type of dislocation, whether it is edge dislocation or screw dislocation, and what is the relative proportion. All of these things you can try to understand just by fitting this curve with different kind of functions, and then understand various sources which are causing this broadening, and which helps you to fit these curves basically. And this process, as I said, is peak fitting is called, many a times it is called XRD LPA, X-ray diffraction line profile analysis, or Rydberg refinement, and various other names are available. But all of them basically tries to understand what causes this broadening. So, that is the importance of this peak broadening here. Okay. So, the first source of broadening, before we go into the material itself, we must discuss and understand one of the sources which is basically coming from the instrument itself, the entire instrument, the instrumentation itself. So, the first source, as we can already understand, is basically in the entire Bragg's condition we have taken n lambda equals 2d sin theta, and we said that lambda is fixed. What if the lambda is not fixed? Because this is what happens in a real X-ray diffraction conditions. The beam is never monochromatic. The monochromatic beam, usually the monochromatic beam we try to capture is a strong K alpha component. Basically this, if you imagine, this is a molybdenum K alpha at 35 kV. So, this strong K alpha component, and it passes through a filter. Even with that, even if we pass it through a filter, what we will be finally getting is a range of lambda in the monochromatic beam. It will not be a perfect monochromatic beam, it will have a range of this angle, and that is related to basically this width of this K alpha itself in the 2 theta, in the wavelength axis. The K alpha peak will have, or the K alpha radiation will have some finite width. That means, in the X-ray beam which is finally falling on the specimen will have lambda or with that kind of a range in plus minus direction. It will have some little bit of deviation from the exact monochromatic condition. So, this will definitely then, from Bragg's condition, what it will do, the lambda will change within a range d. If we or if we think that the d is constant for certain region, the material is perfect, no imperfection, nothing. Even with a perfect material, for a perfect material, just because lambda is different in the source itself, then we will have different sin theta values, and the peak itself will get broadened by a certain amount, little bit of amount. Just because lambda is getting within a range, we are not getting a perfectly monochromatic beam, we are getting it within a range. Our peaks, X-ray diffraction peaks, will also get slightly broadened because of this instrumental source. Now, if we put some values and try to understand that how much broadening we can expect from this, we put something like 0.001 angstrom for this perfectly monochromatic beam, the wavelength range, which is very typical for most of the X-ray sources that we use, moly, copper, chromium. Most of the beams K alpha usually have a wavelength range of 0.001 lambda. So, if we put that, the kind of width, increase in width we can expect is 0.08 degree for lambda. If lambda value, if we take 1.5 angstrom, and theta value we take it around 49, that means 2 theta is around 100 degree. So, at this kind of a 2 theta level, what we can get a width increase of around 0.08, which is for most of the practical purpose is very small compared to other sources. If we take other sources of broadening, line broadening usually is very less, and people uses various other kind of filters so that the line broadening they could bring it down even to that kind of a level, less than 0.1, even less than 0.1 degree, and that is really small for most of the practical purposes. Another problem other than the monochromatic beam from instrumental sources, another problem that happens is that what we use is not a parallel X-ray beam or not a polarized X-ray beam, perfectly polarized X-ray beam. So, that itself will we have seen in the polarization factor, Lorentz polarization factor, it causes a problem. Moreover, if it is not a parallel incident beam, is not a parallel X-ray beam, if it is a combination of divergent and convergent X-ray beams, that itself will cause more broadening, because then the exact Bragg's condition will not be satisfied for this parallel diverging, or it will be only satisfied for a parallel beam with a particular lambda value, but for other kind of beams like divergent or convergent beams, that will show certain intensity for non-Bragg's angle, non-Bragg angle conditions, and there it will finally result in some width increase of the width of the X-ray diffraction peaks. Normally, this again we rectify this by using some kind of special attachments which are known as anti-scatter grid. We are not going into that. Basically, these are kind of grid through which the X-ray beam goes through it, and it becomes a parallel X-ray beam. So, a divergent or convergent X-ray beam goes through this anti-scatter slits, and this anti-scatter finally they will become a plane polarized beams. So, this way we can even reduce the line broadening to a much more extent. So, from this we understand that the broadening of the peak can also happen because of the instrumentation aspect of it. Fortunately, in modern days the X-ray diffraction machines that we use are corrected in such a fine way that you tend to get very little line broadening. And line broadening, remember one thing, if we, as we said, when we were trying to fit this curve and try to understand various sources of broadening, we do not expect the line broadening to come over here, because if that is present and a huge line broadening is present, we have no ways to identify that or to take care. In most of the refinement methods that we use, we do not have a correction, or it does not, there is no formulation for correcting the line broadening. So, we must correct it online, we must correct it using the hardware part, and those are the hardware parts. As I said, we use different type of filters, anti-scattering grid and all, and usually after using this the line broadening comes down to very low value. We can safely neglect that for most of the diffraction experiments, this kind of refinement experiments or X-ray diffraction experiment. So, with this we stop it here, and we discuss about the crystallite size effect in the next class. Thank you.